this video, I'll discuss the volume of similar shapes. Now, in example 1, we're given that shape A dash is an enlargement of shape A. So before I start working out the ratio of the sides and the ratio of their volumes, let me first of all include the measurements of the shapes. So here we have one, and then 3 and 2, and here we have 2, 6 and 4. So basically by looking at two corresponding lengths, and when I talk about two corresponding lengths, that will be that and that, we can be able to find the ratio of the sides. So the ratio of the sides here will be equal to 2 over 1, which is just 2. And then the ratio of the volumes, those ones can be found by calculating the volumes of each shape. So for this one here, the volume will be equal to 1 multiplied by 3 multiplied by 2, which is 6. And for this one, the volume will be equal to 2 multiplied by 6 multiplied by 4, which will be equal to 48. So the ratio of the volumes will be 48 over 6, which is equal to 8. And just remember that 8 is equal to 2 cubed. So keeping that in mind, you can see that, the relationship between the ratio of the sides and the ratio of the volume is that if you cube the ratio of the sides, you get the ratio of the volumes. So let's find out if the same relationship exists with the shapes in example 2. So in example 2, again, we have two cuboids, and the lengths are 1, 3, and 2. And here we have 3, 9, and 6. Let's just work out the volume of each because we need the ratio of the volumes. So the volume here is the same as the first one, which is just 1 multiplied by 3 multiplied by 2, which is 6. And the volume here will be equal to 3 multiplied by 9 multiplied by 6, which is 162. So the ratio of the sides here will be equal to 3 over 1, and we just need to look at the corresponding sides here. So that will be 3 over 1, which is 3. And the ratio of the volumes will be 162 divided by 6. And that will be equal to 27. Now just remember that 27 is the same as 3 cubed. And again, we can notice that the ratio of the volumes here is the cube of the ratio of the lengths, or ratio of the sides. So the same relationship exists in example 1 and example 2. Yeah, we can see here that, the ratio of the volumes is cubed. Here, the ratio of the volumes is cubed. So let's find out with one more example, and then we can generalize this. So in example 3, and we have cuboids again, the lengths are 1, 3, and 1. And here the lengths are 4, 12, and 4. So the volume for this will be equal to 1 multiplied 3 by 1, which is just 3. And the volume for this will be equal to 4 multiplied by 12 multiplied by 4, which will be equal to 192. All right, so what are the ratio of the sides? So the ratio of the sides is just 4 over 1, which is 4. And the ratio of the volumes will be 192 over 3, and that is equals to 64. Now just remember 64 is same as 4 cubed, and again we can see that a similar relation exists here, that actually if you cube the ratio of the sides, you get the ratio of the volumes. So let's generalize this in a statement. So in general, we can say that the ratio of side, so basically a ratio of a side, so ratio of sides cubed will be equal to the ratio of the volumes. So the ratio of the sides cubed is equal to the ratio of the volume. And this is always true, as you can see in example 1, 2, and 3. So moving on, let's apply this in problem solving. So in number 1, it's given that the ratio between two similar solids is 2 to 5. What is the ratio between the solids? So, well, the ratio is just as given, but I'm just going to write it as a fraction. So A, ratio of lengths is equal to 5 over 2. So the ratio of the areas will be equal to 5 over 2 squared, which is equal to 25 over 4. And then part B, the ratio of the volumes will be equal to 5 over 2 cubed, which will be equal to 125 over 8. So for the ratio of the areas, I know this is something that I discussed in the previous video, and basically to find the ratio of the areas from the ratio of the lengths, you just square that to find the ratio of the areas. And we've just seen that to find the ratio of the volumes, you cube the ratio of the lengths. Number 2, a shape has an area of 15. What is the area of similar shape with lengths that are 3 times? Yeah, so the lengths are 3 times the corresponding lengths of the first shape. So that should give us a hint of what the ratio of the lengths are. So basically the ratio of the lengths will be equal to 3 over 1, which is just 3. Or you can just say, because it's 3 times, you can just say it's 3. Now, because we are given the area of the first shape and we want to find the area of the new shape, we need to find the ratio of the areas. So the ratio of the areas will be equal to 3 squared, which is equal to 9. So basically the area of the new shape, will be equal to 9 multiplied by the area of the original shape, and that will be equal to 135 centimeters squared. Okay, number 3, a brick has a volume of 300, and what will be the volume of a similar brick whose lengths are twice the corresponding, and again here the keyword is twice, and B 3 times. Okay, so for part A, clearly we can see that the ratio of lengths is 2, and basically we are trying to find the volume of the new shape. So we need the ratio of the volumes. So the ratio of the volumes will be equal to 2 cubed, which is 8. And basically what that means is that the volume of the new shape is 8 times the volume of the original shape. So new volume will be equal to 8 multiplied by 300, which is equals to 22,400 centimeter cubed. So we'll apply the same approach for part B. Ratio of lengths will be equal to 3. So the ratio of volumes will be equal to 3 cubed, which is 27. And what that basically means is the volume of the new shape will be 27 times the volume of the original shape. So new volume will be equal to 27 multiplied by the original volume, which is 300. And if you work that out, that will be 8,100 centimeter cubed. And that's basically how you work out that question. Number 4, we have a tin of paint, which is 6 centimeter high, and this tin holds half a liter of paint. Now, what you have to understand here is that a liter is a metric unit for volume. So, not a liter is a metric unit for volume. So this is a metric unit, basically a unit of measurement for volume. So think of liters as volume. So the ratio of lengths will be equal to so a similar tin is 12 centimeters high, so that will be 12 over 6, which will be equal to 2. And what you're interested in is in volume, so we need to find the ratio of volumes, which will be equal to 2 cubed. That will be 8, which means the volume of the new shape is 8 times the volume of the original shape, original tin. So new volume will be equal to 8 multiplied by a half, because the original tin can only hold a half a liter of paint. Remember our units here in liters, so this will be 4 liters. That's basically how you solve that question.